Professor Qizheng from Peking University, who is going to give a talk on the Chow ring of Hilb K3 revisited. Okay, please.
Thank you. Thank you very much for the introduction and thank the organizers for the invitation. So it's my honor to speak here. And the topic I am speaking about is about the Chow ring of the Hilbert schemes of points on the K3 circle. So, so as you see, it's a very specific problem, and so I'd like to motivate it a little bit. But before we start, let's just fix some notation. So in my talk, the Chow ring of algebraic cycles will be with Q coefficients, and I use A exclusively for abelian variety, and S for mostly for K3, and X will be mostly a hyperkähler variety. So that's the notation. And let me start with the background, and it concerns only abelian varieties. So this is the classical story. I take A to be an abelian variety of dimension G. Since it's an abelian group, I have the multiplication by n map, which is just you add n times the same point. So this n bracket is multiplication by n. Can you see this clearly?
Yes.
And once you have this map, then Beauville says that you can actually decompose the Chow groups with respect to this multiplication by n map. So you have the decomposition like this with the second index S. And the second index S stands for the fact that, so when you take a class and you apply it by the multiplication by n, and you collect all those classes which are just eigenvectors with respect to this number, n to the power of 2i minus s. And actually, so this is the decomposition into eigenspaces with respect to the multiplication by n for all n simultaneously. So this is the eigenspace decomposition. So this is a very interesting structure for the Chow ring of abelian varieties. And I'll just briefly explain the proof. The proof goes via the Fourier-Mukai transform. So this is the standard thing. You take the abelian variety across its dual, and then the two projections. And then over the product, you have the Poincare line model. And then what you do is you pull back a class with respect to the first projection, intersect with the Chern character of the Poincare line bundle, and then push forward via the second projection. So this is really a downgrading from the derived category to the level of Chow groups. And once you do that, then Beauville realized that so this Fourier-Mukai transform will send this particular component with subindex S to the component where the codimension really depends on S. And then that gives you an algorithm to determine what should lie in this component with index S. You just apply the Fourier-Mukai transform to classes, and then you will get classes of different dimensions. There are different codimensions. So this codimension depends on S. And then you just collect different pieces with different codimensions and then apply the inverse transform back to get this decomposition. So this is the recipe here. And a key feature of this decomposition is multiplicativity. This is really the important thing that I will talk about. And it's actually very easy for abelian varieties. So it says that when you intersect two components of, so with subindex S and T, you only land into this component with index S plus T. So this is easily explained by the fact that this multiplication by n map respects the intersection product. So when you take multiplication by n, upper star of the product of two classes, you just get multiplication by n, upper star alpha, and multiplication by n, upper star beta. Then you just compare the different eigenvalues to see that you only get, so the intersection only land in this piece. In particular, this means that the Chow ring of an abelian variety, once you take the Beauville decomposition, you get into a decomposition into a bigraded ring. So there's a bigrading which respects the intersection product. So just to illustrate how the indexing works, so it might take some time. Let me draw you this picture. I like this picture very much. So so I have two indices, the upper I and the lower S, and all the boxes are indexed this way. So upper I and lower S. And the way I arrange those boxes is for the S variable to go into the y-axis. And then if you want to collect the codimension, then it's from upper left to lower right. So so this is Chow 0, Chow 1, and Chow 2. This is done this way. Just for example, if you're interested in divisors, so this is the Chow 1 part, and then there's the Chow 1 lower 0. This is when you apply, say, multiplication by -1, you get the identity. So this is -1 to the 2. So you get the identity, and these are the symmetric divisors. And then the rest is just so the Chow 1, 1, this is the isomorphic to the Pig 0, and of course with Q coefficients. So that's how the divisors are divided. And so this is like a pyramid-shaped thing, and the reason for this is the Fourier-Mukai transform. So so let's suppose that my abelian variety is principally polarized, so the Fourier-Mukai will be a self-correspondence, and then this Fourier-Mukai transform just is the symmetry with respect to this middle axis. So this is the Fourier-Mukai transform. So you see the symmetry comes from Fourier-Mukai. Yes, that's the picture I want to show you. But when I draw this picture, I'm actually cheating a little bit because they're hard questions that people are not able to answer. First of all, actually the index range given by the Beauville decomposition doesn't necessarily exclude things things on the bottom. So if you view this as a pyramid, then there might be a priori some basement components. So you don't know for sure that the things on the basement are not there. But of course, you know that the fundamental class of codimension 0 has no basement, and the divisors has no basement. So you, by Fourier-Mukai, you exclude some of the parts, but maybe in this 5-dimensional case, the problem already appears here. So you don't know whether you can exclude this. And this is one of the, so this is part of the Beauville conjecture, which is really hard. So the conjecture says that there shouldn't be any basement. And also, if you focus on the ground floor, then this ground floor should sit inside a cohomology by the cycle class map. So if you look at the ground floor, and then all these components should inject into the cohomology of the abelian bracket. And the reason to pose these questions is because one believes that this Beauville decomposition should realize the so-called block valence infiltration in a nice way. So it is believed or expected that so when you take Chow upper IA and with second index greater than or equal to S, and this should be the block valence infiltration. So this is maybe Fs. So this should be the block valence infiltration on the Chow. And I must say here that the block valence infiltration is expected to exist for all smooth projective varieties, but in practice it's extremely hard to construct such a filtration. And this is one of the most important questions in the study of algebraic cycles on varieties. Just to draw a picture how one should think about this block valence infiltration. So so the thing is, you start with the Hodge diamond. So you draw a Hodge diamond. Actually, I put the Hodge diamond to bed. So this is my Hodge diamond. So I flipped it. And then you remove half of the Hodge diamond. I don't need this part. And you take the remaining half, and then the block valence infiltration should be a filtration on the Chow, and it should correspond to the Hodge filtration. So inside the Hodge diamond. In particular, this is, if you believe the Beauville decomposition realizes the block valence infiltration, then it's really a filtration by the floor number. So you have F0 is all the floors, and F1 is starting from the first floor, and F2 is starting from the second floor, and so on. And there shouldn't be any basement. And that's the belief here. But unfortunately, this question is really hard. And it's so hard that there's not even a single example known for any of, so for either of the statements, so the basement statement or the ground floor statement. As I said, the basement statement happens first in dimension 5, so you can take so your favorite elliptic curve and take it to the 5th power, and then the question remains open. So there's no example known for such a system. But in any case, you have this nice decomposition due to Beauville, and you just have to satisfy a bunch of conjectural properties to make it really the nice candidate for the block valence infiltration. I should also mention that for most varieties, the filtration really is only a filtration. It's not, there's no way to canonically decompose, so make it into a decomposition. But as you saw in the case of abelian varieties, you get more than just a filtration. You really have a way to canonically decompose it into a nice decomposition. And in a way, you have a way to canonically split this filtration. So this is this decomposition is a canonical splitting. So this is what we get from abelian varieties. So apart from these hard questions, you may ask some easier questions that might have an answer. For example, there's this question asked by Voisin, and it was answered by Mullen and O'Sullivan independently. This is when you take only the symmetric divisors, and you know for sure that those symmetric divisors live on the ground floor, right? And then you take all polynomials of those symmetric divisors and they form a subring of the Chow ring, and even the Chow living in the ground floor. So then you can ask, instead of asking that the entire ground floor should sit inside cohomology, you may ask the subring whether it sits inside cohomology, whether the cycle class map is injective. Here, the answer is yes. So you can say that all polynomials, so the space of polynomials of symmetric divisors really sits inside cohomology. That's one thing that does have an answer. So let's move on from abelian varieties to the next subject, which is about K3 surfaces. So my S will be a projective K3 surface. And then there's this also classical result of Beauville and Voisin, where they say, okay, on the K3 surface, you can find a distinguished zero cycle class. So I'll label it C. So this is a class in the Chow group of zero cycles on the K3 surface. And you can take it just to be a class represented or supported on any rational curve on the K3 surface, and they will all represent the same class. So so once you have this class, there are two results. So first is that whenever you intersect two divisors, a priori you land into the space of zero cycles, which is really big. So this is an infinite dimensional vector space. This is the result of an old result of Mumford says that this really is infinite dimensional, even in a much stronger sense. But then the result says that whenever you intersect two divisors, you always land in this one-dimensional subspace generated by the distinguished class. So this is kind of a special property. And the second statement says that you have the tangent bundle of the K3 surface. You can take the second Chern class of the tangent bundle. And you know the degree of this second Chern class is 24 because that's the Euler characteristic. And then the result says that it's exactly 24 times this one class C. So so this is, again, you're living in an infinite dimensional space, and this is just one dimensional subspace, and the second Chern class lives exactly here. So this is the result, and you can just run an easy test whether this result holds in much more generality or it's really specific for K3s. Actually, it's quite specific in the sense that if you take the K3 and you blow up a wrong point, so any general point, very general point, let's say, and then the result will not hold. Because a very general point will have another class in the Chow group of zero cycles, and then you can intersect something with the exceptional divisor, then you land in some other dimension. So this result itself is very fragile. It's quite specific. Again, I try to illustrate the result with this picture, but as you see, the picture is much more boring than the abelian variety case. And partly because the K3 surface has no odd cohomology, so you have fewer boxes and also you have fewer dimensions, of course. So so there's the Chow 0 and Chow 1, both trivial. The Chow 0 is just a fundamental class, and the Chow 1, all the divisors. And the only interesting thing happens in Chow 2. So I split them into two parts. One is the Chow 2 0, so lower index 0, which is this one dimension given by this distinguished class. And then there's the Chow 2 lower 2, which is all the zero cycles of degree 0. So that's the complement. And then I can reinterpret this result of Beauvais-Voisin. The first thing you see from this box picture is that whenever you multiply two divisors, so you go from upper 1, lower 0, directly to upper 2 and lower 0, and nothing more. So this direction is unique. And that is the multiplicativity, similar as the abelian variety case. So you take Chow upper I, say lower S, so lower 2S, upper J to lower 2T, and you only land into this thing with a lower 2S plus 2T and nothing more. You don't get to reach the other component here. And the second statement of the Beauvais-Voisin theorem says that if you take the second Chern class of the tangent bundle of the K3 surface, it will live on the ground floor only. So this is sub-index 0. And so in this sense, the K3 picture is very similar to the abelian variety case. And then the main topic today, and also the main question that one may ask is whether this is just a sporadic thing, or is there some pattern? For example, why you expect the same phenomenon for K3 as in the abelian variety case. So then the natural question is to search for higher dimensional analogs of the K3 phenomenon. And then you have two obvious candidates, the Calabi-Yau or hyperkähler. And it didn't take much effort for Beauvais to figure out that the Calabi-Yau doesn't work. So he found counterexamples to this property. And then the remaining candidate is the case of hyperkähler variety. So from now on, I'll focus on hyperkähler varieties. And I'll just take the hyperkähler variety of dimension 2n, and this is my x. And just to recall that this x is non-singular projective, simply connected, and the space of holomorphic two forms is generated by spanned by this non-degenerate holomorphic two form. So then again, you want to ask questions similar to both the abelian variety case and the K3 case. So first of all, you want to ask whether there's a meaningful multiplicative decomposition of the Chow ring of X, which has the same shape. And here by meaningful, I again mean that it should split the block-Beilinson filtration. More precisely, this FBB upper S should be the Chow of second index greater than or equal to S. Like this. So you look for this such a decomposition, and it has to be multiplicative. Then also you may ask whether there's a basement, and you expect no, and also if you believe the block-Beilinson filtration exists and you find it's splitting, then the ground floor should again sit inside cohomology. These are the hard questions. And then you can also soften the question a little bit by asking not the entire ground floor, but only things you are familiar with. For example, you know that hyperkähler varieties, there's no H1, so there's no peak 0, so that all divisors should live on the ground floor. And then you just pick all the divisors and take all the polynomials of the divisors sitting inside the Chow. And then you can ask whether the sub-ring really sits inside the cohomology. So I know divisors are on the ground floor for sure, and then I ask whether all the polynomial relations in cohomology already hold on the level of Chow. So this is the so-called Beauvais conjecture. And then you can enhance this conjecture a little bit, make it stronger to add all the Chern classes as well to the ring that you know you expect that to live on the ground floor. So yeah, add all those Chern classes to the divisors and ask for all the polynomials, whether this ring will sit inside cohomology. So that's the Beauvais-Buzan conjecture. It's like a stronger version. And the main theorem of today is joint work with Andrei Negutz and Georg Oberdick, is to say, so we are trying to understand one of the hard questions, which is the existence of the meaningful multiplicative decomposition, but only in the case of the Hilbert scheme of points on the K3. So this is like a very specific example, but also the classical example of hyperkähler varieties. So we're able to show that for the Hilbert scheme of points on the K3, there is indeed a natural multiplicative decomposition of exactly the right form. Here, since the Hilb K3 has no autocohomology, the second index will be labeled by even numbers. So it's exactly the decomposition proposed or expected by Beauvais and some others. So this is what we have. And the key here is that our decomposition is multiplicative as well. And then the second statement is that indeed, with respect to our decomposition, all the Chern classes live on the ground floor. So maybe you can't see this clearly, but this is the ground floor here. So they're all as expected. So that will be our main theorem, and I'll just tell you how we obtained this and what's the idea behind it. But before we go to our approach, let me discuss a little bit how previous approaches were. And all these results were obtained before or in 2015. So there has been a lot of progress before that, but after 2015, not much was known. And there are basically two approaches to these questions. First of all, there's the approach of Mingming Shen, Xiao Liang, and they were aiming for more general hyperkähler varieties. And their idea is also very natural. They were trying to develop a theory of Fourier-Mukai transforms for hyperkähler varieties. So to get a Fourier-Mukai transform, you have to find a Fourier-Mukai kernel. In the abelian case, it was the Poincare line bundle. And in the hyperkähler case, they proposed to use the so-called Beauvais-Bogomolov-Fujiki form as the Fourier-Mukai kernel. So this is the form that is associated to every hyperkähler variety. It's the form on it's a symmetric form on the second cohomology of the hyperkähler. So since it's a form on H2 of X cross H2 of X to some number, and you can take its dual. So to get a form on H lower 2, so you also get a form on H lower 2 cross H lower 2 to some number. And then this will respect the Hodge structures, and eventually it will give you a Hodge class on H4 of X cross X. And then to use this as the Fourier-Mukai kernel, one first obstacle is to show the algebraicity of this class. This was indeed achieved for the Hilbert schema. So for K3 n-type hyperkähler varieties, this is okay. This is a result of Markman. So you know the class is algebraic, but then afterwards you have to normalize it to make it, in a sense, living on the ground floor of the product, so that it doesn't mess up with the flooring. It's a bit similar in the abelian variety case. You have to normalize the Poincare line bundle so it's trivial on the zeros on both sides, and only after that this Poincare line bundle will not mess up the flooring. So here you have to find a way to normalize this algebraic class in Chow to make it behave nicely. That's the second difficulty. But the main issue, so this is like, I would say this is a fatal issue for this approach, that this Bogomolov form is a symmetric form on the H2, so it lives on the second symmetric power of H2. Somehow it will not be able to see anything beyond the symmetric tensors of H2 inside the cohomology of X. So this is at the level of cohomology. Then at the level of Chow, it will not be able to see much for classes or for cycles governed by the complement of the symmetric power of H2. So if you take this one, the orthogonal complement, then this Fourier-Mukai transform will not tell much about it. So in particular, this Shen-Viao approach, modulo all the difficulties, it works well for Hilb 2 of K3, because then the symmetric tensors of the second cohomology is the entire cohomology. But starting from K3 3 type, then you don't expect it to work well to get a full expected decomposition. So this is so much. This is the general approach, and then there's the more specific approach only for the Hilbert scheme of points on the K3, and this was proposed by Voisin, Viao, and Lie Fu, and my colleague Zhu Tian for the Hilbert scheme of points on the K3. And also there's a parallel story for the generalized Kumers of an abelian surface, so that A is an abelian surface. Yeah. So in this case, things are more explicit. So first of all, there actually is a candidate of the decomposition for the Hilbert scheme, but only as a group. So there's a group, you more or less know how to decompose the Chow of the Hilbert scheme. And this is because there's the earlier work of De Cataldo and Miorini, where they showed you can naturally embed the Chow ring of the Hilbert scheme inside the Chow ring of all the powers of the K3 surface. And then on all the powers of the K3 surface, you have more or less a Chow version of the Quenet decomposition, so you know how to decompose the Chow. And then you just restrict to your Hilbert scheme. And that is a decomposition at the level of groups. So now the key thing to verify is multiplicativity, whether this decomposition respects the intersection product, whether the bigrading respects the intersection product. Then to recover multiplicativity, they have to reduce the problem to some identities at the Chow level involving the third diagonal, the small diagonal inside the third power of the Hilbert scheme. So this delta 1, 2, 3 is the small diagonal on Hilbert scheme cross Hilbert scheme cross Hilbert scheme. And the reason is that this third diagonal effectively controls the multiplication or the intersection product. So whenever you have an alpha and a beta and you want to intersect two of them, then you know that it's the pullback of alpha with respect to the first projection, a pullback beta with respect to a second, and then intersect with delta 1, 2, 3, and after all you push everything forward by the third projection. That's how you get the intersection of two classes. So you have to verify that there's some identities for this small diagonal to satisfy, and then you have to verify them at the level of Chow. But then the issue is it's very hard to compute this small diagonal. So especially one would hope to have a formula for the small diagonal in terms of classes we know inside the Chow of the powers of the K3, but there's no formula, explicit formula for this yet. And then there are some approaches by Voisin to formulate some universality for these natural classes to get around any explicit formula, but somehow the theorem was announced around 2015, but the proof hasn't appeared yet. So there's this issue here. So then that's the situation around 2015, and now our approach is so we're trying to find a new approach without all the issues of the previous ones. So our idea is to go back to the case of abelian varieties and think about this decomposition that Beauville obtained. It's really an eigenspace decomposition with respect to the multiplication by n. And we're trying to look for a similar eigenspace decomposition, but we have to find the right replacement for the multiplication by n map. And this new replacement has to be able to see the entire cohomology or the entire Chow, not only the part that's governed by the symmetric powers of H2. So already at the level of cohomology, we need some new input that can tell everything about the entire cohomology of the hyperkähler. So as many of you know, that people always say that hyperkählers are easy, and the entire cohomology, where all its geometric properties are essentially controlled by the H2 of the hyperkähler, because there's the global Torelli theorem and a lot of other things that can be expressed in terms of H2. But more specifically, if you want to know about the entire cohomology in terms of H2, the only way I know that you can say precisely how the cohomology is controlled by H2 is through this result of Verbitsky. So that so far, I think this is the only thing that, so only result at the level of cohomology that tells how everything's governed by H2. So the result says that the cohomology is indeed controlled by H2, but in a more sophisticated way. It's controlled via a certain Lie algebra action And this is the so-called, now it's called the Lund-Verbitsky Lie algebra. Because the same result was also obtained independently by Loingha and Lund. So there's a natural Lie algebra action on the entire cohomology of the hyperkiller, and it's simply the Lie algebra generated by all SL2 triples, all things satisfying hard lattice. So all things satisfying hard lattice, for example, ample divisors and more. So you put all things satisfying hard lattice into this Lie algebra, and this is what you get. Then there's a result telling you which Lie algebra this really is. And I think the best way, this is really just an idea. I think the best way is to understand what this Lie algebra is to think about an artificial or hypothetical surface. So this is an imaginary surface. And this doesn't exist in reality. And the surface is a regular surface. There's no odd cohomology. Of course, there's the H0 of the surface generated by the fundamental class. And the H2 of the surface is the second cohomology of the hyperkiller. And then the H4 is, again, this volume form. So it's nothing much. And then the key is to define the intersection of two classes in H2. So if I take two classes in H2, I want to tell what the cup product is. Then the cup product is given by the Bogomolov Fujiki form. So this is the BVF form. But the two classes times the class omega, the volume. Yes. And once you have this hypothetical surface, you know that it itself also has this Lie algebra action generated by all SL2 triples. And then in the end result is that this Lie algebra for the hyperkiller is the same as the Lie algebra for this hypothetical surface. And it's exactly the special orthogonal Lie algebra with respect to this lattice. This is the lattice H2 of the hyperkiller with respect to the BVF form, and then this the lattice 0, -1, -1, 0. So this is like the Mukai lattice for the hyperkiller. And then the Lie algebra is the special orthogonal Lie algebra with respect to the Mukai lattice. And this is the best we can say about how the H2 controls the entire cohomology. And from this point of view, I think that this is really the right thing to look at if we want to get a nice decomposition at the level of Chow, which reflects the entire cohomology of the hyperkiller. So this is what we know in cohomology. And the next step is to lift some of these structures to Chow. Of course, we will not be able to look at all those transcendental things inside this Lie algebra. So we can only take the algebraic part, which is, I will call the G Néron-Sévère, which is generated just by, say, all the SL2s coming from ample divisors, let's say. And this is a sub-Lie algebra. And we look for liftings of the sub-Lie algebra action from cohomology to Chow. So this is a lifting from cohomology to Chow. And if you believe some general theories, then this lifting has to exist for hyperkiller varieties. It's part of the Beauvais-Voisin expectation. And it has to exist, and once it exists, it has to be unique also. So and that's the thing you're looking for. We don't have a general recipe for the lifting, but in a special case of the Hilbert scheme of K3 surfaces, we do know how to lift the algebra action. So for Hilb, there's this result by my collaborator Oberdi, which says, okay, there's an explicit way to lift this Lie algebra action to Chow. And it's very explicit in terms of the natural Nakajima operators. So this is something specific for Hilbert schemes that's not available for more general hyperkähler varieties. So Oberdi gives the formulas, explicit formulas for all the Lie algebra action in terms of Nakajima operators. And once we have that, in particular, you can immediately show there's this soft question of Beauville, whether the space for all polynomials of divisors really sit inside the cohomology. And then the answer is yes, because the space generated by all divisors is just this Lie algebra acting at this fundamental class. So, so this is immediately an irreducible representation of this Lie algebra because it's just Lie algebra acting on this one class in degree 0. So if it contains this one class in degree 0, it has to contain all. Since it's irreducible, there cannot be more relations in cohomology than in Chow. And then the Schur lemma will just tell you that it has to be an injection. So this has to be injected. So that's already nice to have. Of course, we only have it for the Hilbert schemes. That's a part where we have to specialize to the case of Hilbert schemes. But we do believe such a lifting exists for general hyperkählers, and maybe the next thing to try to test is when X is, say, a moduli of sheaves on a K3 surface, but we don't know the answer yet. Sorry. Okay, so then the next step is, sorry. Can you still see my screen? Yes. So the next step is really the crucial step is how we get the decomposition. This is that inside this specific Lie algebra, there's a nice thing that lives. So there's the canonical thing that lives here, which is part of all the SL2 triples. So whenever you have an ample divisor, you have this grading operator H. So this is the grading. And this guy is really important, is crucial. That will be our replacement for the multiplication by n. And the way we get this decomposition is again an eigenspace decomposition with respect to this grading operator. So here's the precise definition. So for convenience, I have to introduce an H tilde, which is simply just H plus 2n times the identity. And the reason for this is that I want the grading operator to live in a range 0 to 4n. So I don't want it to be around 0, but I want it to be around 2n, just to make all the things positive. And then the decomposition really is the decomposition into eigenspaces with respect to this H tilde. So this is the eigenspace decomposition. And that's how we find our replacement for the multiplication by n. So this is a grading operator, but it's an operator on Chow. And we're able to decompose the entire Chow into eigen subspaces with respect to this grading. So, so that's maybe just one last thing. So this is the decomposition we obtained, but we can also show that it agrees with De Cataldo and Miorini. Yeah. So this is what we have. And then the final thing, of course, it's no surprise that we have decomposition at the level of groups. The really interesting or the crucial thing is multiplicativity. So there's a way we use this grading operator to test the multiplicativity of our decomposition. And the test is simply to test, say, the grading of the product of two classes with respect to the grading of each of the classes. It's just like how we prove multiplicativity for abelian varieties. You have the multiplication by n, and it respects the intersection problem. So here for us, we need this grading operator h tilde to satisfy the h tilde of alpha intersect beta should be the same as h tilde alpha intersect with beta plus alpha intersect with h tilde beta. And in particular, in other words, this is a derivation. Yeah. And once you have this, then you can easily compare the eigenvalues to see that the multiplication, the intersection product does respect our grading. So this is how you find a way to test whether the decomposition is multiplicative. So a convenient way to rewrite what we have here, what we want, this derivation identity, is I write it into a lead bracket. So what I do is that I move this part to the left, and you will see that this is the commutator between h tilde and the multiplication with the class alpha applied to the class beta. And then the right-hand side will be the multiplication with the class h tilde alpha. And that's what we want. If we have this identity, then we're done with multiplicativity. Now, in practice, what we show is something similar. So this is the key result we show, is the multiplication by h and the commutator between the multiplication by h and the commutator between the h tilde and the multiplication by alpha is indeed equal to the operator of multiplying with another class. Let's call it gamma. And this gamma is very explicit. So we have explicit formulas for this class gamma in terms only in terms of the class alpha. So whenever you have an alpha, I can tell you what gamma is. So there's an explicit formula. So let me call this formula star. And then let me tell you how this star is enough to get multiplicativity. So you look at this formula star and you apply it to just the fundamental class in Chow 0 of the Hilbert scheme. So this is the fundamental class 1. And on the left-hand side, you get h tilde and alpha multiplied by 1. So this is the h tilde of alpha. Minus alpha and then h tilde applied to 1. And it's easy to show that this part is 0. And then the right-hand side is just the multiplication by gamma to 1. So it's gamma. And then you find immediately that gamma is indeed the h tilde of alpha. So So in particular, this formula star gets back the thing we want. So this gets back this formula we want. In particular, this proves multiplicativity. But also, since our gamma is really explicit in terms of alpha, we do have an explicit formula for the h tilde of alpha. So if you take any class alpha, there's an explicit algorithm to compute how this operator h tilde acts on alpha. So everything is explicit. In particular, you can use this explicit formula to see when alpha is the Chern class of the Hilbert scheme, and that's how we find out where the Chern classes live, and indeed they live on the ground floor only. So this is what we have. And maybe just one more thing. To explain the proof, how the proof of this formula star goes. We have to do a lot of explicit calculation, and that's a bit unfortunate, but we have to do that. And the calculation is done in terms of two sets of generators of the Chow ring of Hilbert scheme. So I've already mentioned the first set. This is via the Nakajima operators. So you have the standard construction so this is the space Hilb n plus k. And this is a pair of two ideals, one contained in the other, such that the quotient is supported on a single point. And then you have three natural maps, one to Hilb n, another to Hilb n plus k, and the third to the single point that you specify. And then the Nakajima operators, one way to write them is to take, for example, the pullback via the pullback via this, and then the push forward via the two other projections. So that gives you an operator from the Chow of Hilbert scheme to the Chow of Hilbert scheme cross S. And then one result, which is known a long time ago, that the entire Chow ring can be generated in this way. You can take iterates or just compositions of such operators applied to any class in the Chow ring of some power of the K3 surface, and this will generate all the Chern classes of the Hilbert scheme endpoints on the K3. All the Chow classes. So this is one way to generate the entire Chow, and then there's another way, which is some people call it descendants. This is given by the universal classes on the Hilbert scheme cross S. So the Z will be, it's the universal subscheme. And then you take the universal subscheme, which lives on Hilb n cross the surface, and then you have the two projections. And what you do is to pull back some classes from the, so you pull back some gamma from some powers of the K3, and then you intersect, you hit it with the arbitrary numbers of Chern characters of this, the universal subscheme. And then you again finally push forward to the Hilbert scheme. And that's another way to generate the entire Chow ring of the Hilbert scheme. So the reason we use both is that we, as you saw, we want to compute, so in the previous slide, we want to compute the commutators between this H tilde, which is expressed explicitly in terms of the Nakajima, and then the multiplication with respect to some class alpha. Now, the reason we use both generators is that Nakajimas are really good for commutators. But they're not so good for computing multiplication. On the other hand, the descendants, they are good for multiplication. As you can see from the definition that multiplying with a class of this descendant type is the same as the multiplying upstairs on the Hilb n cross S. So this is a good generator for multiplication. And then since we need both commutators and multiplications, we have to use both, and then we have to find a nice dictionary or nice way to translate the two. So from one to the other. And this dictionary is indeed there, and it's provided in cohomology by Lane and Wei-Ping Li and Qin and Wang. And they have these results in cohomology, and recently these formulas for the dictionary were extended from cohomology to Chow by Malik and my collaborator Neguts. So once we have that, we can effectively carry out calculations and to eventually get this formula started. So that's how the proof goes. So I'm already over time, so I would just say that if you're interested in the motives, then our result can be upgraded to Chow motives. And also we can refine the decomposition in terms of a much bigger, so in terms of the Cartan of this neuron severity Lie algebra. And we can also locate all the Chern classes. So I'll stop here, thank you.
Okay, thank you very much. We have time for comments or questions.
So for the second set of generators, is the result also true for if the hyperkähler manifold is the modular space of a stable sheaf of some Mukai vector, if the universal sheaf exists?
For the second, yes, I think, yeah.
And is there a way to guess whether there's analogous of Nakajima operator among modular space of stable sheaves?
I think Andre Neguts has thought about it for a long time. And I think the conclusion is that you do have also nice operators on the model F sheaves, but they're just not as much as they're not as many as the Nakajima operators. So yeah, it's not clear how well these operators can give you the. So you can also compute some commutator relations, but it's not clear whether they're enough to make all this thing work. Whether, for example, whether they can recover this Lie algebra action, so whether you can write it in terms of these natural operators on model F sheets.
Okay, thank you very much.
Sorry, can I ask a question?
Sure.
Actually, two questions. Sorry, I'm interested in the Chencas, where it located. So, for example, in the C2 in the hyperkähler dimension 4. So, is it possible that not only for K3 case, for your hyper scheme of K3 case, but also Kuma case?
Yes.
Is it possible for the calculation of the C2? For example, in dimension 4.
Yes. You want to know the result for the Kumars, for the generalized?
Yeah, the C2 or the Chencas.
Yeah.
Is it possible exactly calculating that it out?
If you just take the generalized Kummer, you can calculate that. But if you do deformations of the generalized Kummer, then it's not clear how you can obtain the Chow decomposition. How you can apply you can locate the second term class, the term classes.
Okay, and I know very little about the Verbitsky's monodromy birational minimum. I mean, there's a class very similar to the -2 curve in K3. So is that the monodromy birational minimal related to your settings?
I don't know. I'm not sure if I cannot say anything intelligent about this. I'm sorry.
Okay. Yeah. Okay. So thank you.
Can I ask a naive question? Maybe this is not too exact, but so the intuition of a magic surface in your talk, that it kind of indicate a universal pattern of the existence of the algebra structure on other type of hypercalar.
I'm sorry, what was the question?
Oh, my question is the intuition of the magic surface, which say that it probably controls the whole cohomology of any hypercalar variety. So that it also indicate the kind of existence of the algebra structure on any kind of hypercalar varieties.
Well, this result is indeed for all hypercalar varieties. So you don't need any assumption. So you just take a hypercalar variety, and there's always this magical surface, as you say. And
okay.
Yeah. So it's clear how you get the special orthogonal Lie algebra for this magical surface, and the problem is to verify that all the commutation relations you get for the surface that will actually hold for the commutation relations for the hypercalar. And that's the main result of Verbitsky and Loeing-Hamlin's also.
Okay, thank you.
So let me ask you, is the result hold if you do a Mukai flop?
Yeah, so actually there's another result of Urquiza Heats. She proved that whenever you have whenever two hypercalars are birational, their Chow rings are actually isomorphic. So yeah, so there's and it's in a canonical way that they're isomorphic. So yeah.
So also, if your hypercalar manifold already emit a Lagrangian vibration section, a nice one.
Yes.
And so that you have a universal bundle shift over the product. Right? Can you use that to help?
Yeah. So you can use that to get part of the decomposition. I think mostly for zero cycles. So there are various proposals. I think the question was studied by O'Grady and also Fazan, that proposes how you can get this decomposition, at least for zero cycles, with respect to the Lagrangian vibration. But then there are questions to ask whether it's independent of the Lagrangian vibration, and also whether it satisfies all the properties.
Yeah. So are we using can you use the multiplication, fiber-wise multiplication by n? Would that be operations?
Yeah, that's a very nice question, actually. Yeah. the problem is how one can formulate it in a precise way. I think maybe one should start with an elliptic surface, elliptic K3 surface to see whether this Beauville-Voisin result can be achieved by this fiber-wise multiplication by the elliptic curve. So I don't know an answer on top of my head, but this is what's right.
Also, this field, yeah.
In the section, in order to define the multiplication, right? So in general, there's only a multi-section.
I'm assuming you already have a section, let's say. Yeah. That's in a good case, let's say.
Yeah. So regarding Lagrangian fibrations, I think one question which might be interesting is to sort of decompose the Chow with respect to this Lagrangian fibration.
Yeah.
But then you need to lift the so-called BBD decomposition theorem from cohomology to Chow, and maybe you can derive. Yeah, I think the formulation is clear, and that they're the so-called intersection cohomology or intersection motives or intersection Chow, and you can use that to decompose.
I see.
Then I think that's the correct framework to do things this way.
Is there generalization to derived category and non-commutative K3 or non-commutative fabricator?
One interesting question is whether one can generalize this Verbitsky Lie algebra action from cohomology or from Chow to the derived category. Yeah, one can have a categorical Verbitsky Lie algebra action. Yeah.
That would be difficult.
So that would be interesting.
Yeah.
That would be interesting.
Well, excellent talk. Thanks. Yeah.
Okay, so if there are no more questions, let's thank the speaker.
Thank you.
Thank you.